Hello, everybody. This is chapter 2.7. Two more sections left of chapter 2. And today, honestly, it's a little bit similar to what we did yesterday. We're going to be solving proportions again, right? We solved proportions last time. We'll check out my pen. Just like we solved proportions last time. But we're going to extend the idea a little bit and do some things that are a little bit more complex than what the last ones were. We're also going to take a look at what's called a scale drawing, things that builders and architects and engineers use whenever they're constructing something to make sure that their plans match their product. Okay. So today we're going to be using this thing called the cross product, and we actually used it yesterday when we were solving for proportions. So let's just do two quick examples and then look at the scale drawing. So here's our first proportion that we have here. We need to solve for x, right? That one down there, this guy right there. And we need to get it by itself, just like we have with all solving. We're going to use this thing called the cross product to make that happen. And cross products, cross multiply, right? Same basic thing. So we're going to take, we're going to multiply the things on the diagonals by each other. So 6 times x is 6x, and 8 times 15, let's see, 10 times 15, that's 150. So I need to lose 30 from that, 120, right? 250 is less than that, should be 130. Equals 130. And then we're going to divide both sides by 6. No, it's not 130, that's 120. Why didn't any of you correct me? Come on, you can't let me sit up here and do things wrong. You have to correct me when I do something wrong. Jeez. That's 120, not 130. Then we're going to divide both sides by 6 because that's multiplication. The 6 divided by 6 is 1, so it cancels. And that's x equals 120 divided by 6. What goes into it? Well, I know that 6 goes into 12 twice, which means that 6 will go into 120 20 times because you're just adding a 0. So x equals 20. That was very similar to what we did yesterday. So let's do something different that kind of extends this idea a little bit more. So now we have 4 over x equals 8 over x minus 3. So we're going to solve this problem the same way. We're going to use the cross product. I'm going to multiply these together, and I'm going to multiply these together. 8 times x is 8x. 4 times x minus 3, that's 4 times x minus 3. Here's the big key difference. Here's sort of the extension from what we did yesterday. This 4 is multiplying x minus 3, meaning it has to multiply the entire quantity. And so this is 4 times the quantity, x minus 3. So we're going to need to distribute that 4, and we end up with 8x equals 4x minus 12. And notice that I have variables on both sides of the equation now, and so I need to get them to the same side. So I'm going to move the 4x over here. That's a positive 4x, so I'm subtracting 4x. I get 4x equals negative 12. And then finally, my last step, I've got 4 times x, so I'm going to divide both sides by 4. Those cancel out, and that leaves me with negative 3. So notice that our technique here is the same. We're multiplying, we're doing the cross product, we're cross multiplying. And again, you only cross multiply when there's that equal sign right there between them. But this time, we ended up with variables on both sides. We ended up having to distribute one of these things when we multiplied. So there's just a little bit more involved here, okay? But like I said, basically the same as what you did yesterday, same technique. But a little bit more complex. So let's talk about scale drawings. A scale drawing is a two-dimensional drawing of an object in which the dimensions of the drawing are in proportion to the dimensions of the object. A floor plan of a house is an example of a scale drawing. The scale of a scale drawing relates to the drawing's dimensions and the actual dimensions. So major places where scale drawings are used is in any kind of construction. And that actually includes even virtual construction as well. Like if you're doing game design, there's scales that you make to say, well, I'm a character in a video game and I'm walking across the land, right? 1 mile in the video game is going to be equal to like 1 mile in real life. So how do you make sure that the scale of your character matches the correct proportion for what excuse me, for what the actual mile is. Okay. You also do this when you're creating things in something that's like three-dimensional artwork. Again, I think I mentioned this the other day, but right, if you're in Mr. Young's class right now, his engineering design class, which you should take because it's a really cool class, he's doing stuff on 3D printers, where you have a drawing that you're making in a program called AutoCAD, and that scale drawing that you're making in AutoCAD is then going to be scaled up and printed on a 3D printer to make something. And it's a really cool technology that we get to use, and the fact that 3D printers are getting more and more cheap gives us the opportunity to be able to do that. So you kind of check out this idea of a scale drawing and a proportion in those types of classes. It's also done in a floor plan of a house. I used to work in a construction yard, and people would bring in their floor plans, and it was my job to take that floor plan and write up a list of all the lumber they would need, the amount of doors. Like I would write out their entire order by analyzing this scale drawing of a floor plan, and that's how we determined what we were selling. So scale drawings are used a lot. So here's just a quick example, right? When looking on a map, the cities of Cleveland and Cincinnati are 4.2 centimeters apart. So you've got some, land mass. That's a circle. That does that in the actual map. It does a loop like that. And then down here is Cleveland, and up here is Cincinnati. And on the map, this distance is 4.2 centimeters. Now, the scale of this map is 1 centimeter equals 8.5 kilometers. So this is a 1 to 85 map, meaning that every centimeter we travel, it's an actual, in real life, it's 85 kilometers. So what we want to do is write and solve a proportion for the actual distance between the two cities. So setting up this proportion, fairly easy, right? If we have a scale of 1 to 85, that right there is one of our ratios. That's one of our fractions that we're putting in, 1 to 85. And the thing that's important to recognize about this is that this top part is the centimeters, and this bottom part is the kilometers. So when we're setting up the equivalent proportion over here, we know that there's 4.2 centimeters in the actual distance between Cleveland and Cincinnati, right? So that's going to go on top with the centimeters portion of the proportion. And the bottom, the actual distance, well, that's what we're looking for. And so we don't know that, and so we're going to throw that down. So we cross multiply. 1 times x is x. 4.2 times 85. Ooh, 4.2 times 85. I can't do that one on my head. Let's do a quick thing over here. 4.2 times 85. All right. That's 10, 17, 20, 22, 33, 34, 7, 5, 3, and that's 1 decimal point, so 357. So So they are 357 kilometers apart in actual distance, according to the scale drawing of it. Now, this is the same thing, the same kind of process as what you do when you have a scale drawing of a house, right? If you're given the scale drawing of a house, and your house looks like this, right? And that's one room, there's a closet, that's your kitchen over here, you got this great big living room, dining room, whatever. And if this is like one to I don't know 10, right? So like 1 centimeter is 10 feet. Well, I know exactly how long that wall is because if that there is 2 centimeters, then I know that that's 20 feet. And so that's how we determine how much materials we would purchase for a house. Again, this is what I did for a living for about a year and a half while I was in college. So it's a very useful thing to understand. There are lots of different places that you can. All right, that I believe is it for today. Very similar to yesterday. We're almost done with chapter 2. We'll see you later.